Let's look at an application of Stokes' theorem. In this particular case, we have the vector field z squared, comma 2x, comma y squared, and then our surface is just the paraboloid z equal 1 minus x squared minus y squared, which terminates in the xy plane, or z equals 0. So we see that the curve that acts as boundary for this particular surface is just the unit circle. And then of course if we project the paraboloid into the xy plane, we get the unit disk. So again, this characterizes what's going on in a very straightforward manner. And of course we need to compute the line integral of f about c. And of course we're going to use the Stokes theorem to do that. Now the components we need one of the components of the unit normal, and also we need the curl of f. So we're going to do the nabla cross the vector field, and then we're going to execute the same computation we've done many times. But let's go ahead and do the curl here. So notice first we want to do 2, 3, so we're going to do the y partial to give us a 2y, and then 3, 2, which will give us a 0, so 2y minus 0, and then 3, 1 gives us a 2z, and then 1, 3 gives us a 0, and then of course 1, 2 gives us just a 2, and 2, 1 a 0. Notice all of these have a factor of 2, so we'll go ahead and extract that, and we have 2 times the vector y, z, 1. Again, not difficult, but critical. These calculations are critical, and we do need to take our time to make sure they're correct. And then of course, the component of the outward normal that we need will be negative zx, negative zy, and 1. And of course, the x partial here is the negative 2x made negative, gives us 2x. The y partial, a negative 2y made negative 2y, and then of course the 1. And now, of course, if we need to compute the line integral of f about c, we apply Stokes' theorem to do the double integral or surface integral of the curl. And so we go ahead and substitute our curl right here, 2 times the vector y, z, 1, and then our component of the unit normal, 2x, 2y, 1. Now, of course, we can factor this 2 and then just take the dot product. So this will give us a 2xy, a 2yz, and of course a 1. And now since the region of integration is the unit disk, at this point I'm just going to switch to polar coordinates. You can often stay in the Cartesian coordinates and probably do fine, but what we found when we have lots of circular symmetry, the polar coordinates produce integrals that are usually quite straightforward and not difficult at all. And even though you may feel like you're doing a little extra work, the integrals are simple. So this will be a good move. Now, of course, when we do the transformation, we'll replace x with r cosine theta, y with r sine theta, and of course z will just be 1 minus r squared. So this is a very simple transformation. And of course the dA will be r dr d theta, because the Jacobian will be r in this case. And so what we want to do is just go ahead and make that transformation. So with the 2xy, we get 2r squared cosine theta sine theta. And then with the 2yz, we get 2r sine theta 1 minus r squared, which I just simplified here by running all the r's together. 2 sine theta r minus r cubed. And then of course, don't forget the 1 plus the 1 r dr d theta. And now what we want to do is go ahead and multiply by the r. These will give us very simple add 1 divide by the new power integrals. So we get 2r cubed sine theta cosine theta, and then 2 sine theta will get r squared minus r to the 4th plus r. Now we can again do the antiderivative very simply. We'll get r to the 4th over 4. The 2 will absorb into the 4 to give us a half here times the trig functions. And then of course here we get r cubed over 3 and r to the 5th over 5. And here we just get r squared over 2. And now we're integrating from 0 to 1. And of course the 0 just annihilates everything. So all we have to do is worry about the 1, and that's our friend. So of course in the first integral, again, we've got the 2 that we factored. And we just have a factor of 1/2 times sine theta cosine theta. And here we're going to get the 1/3 minus the 1/5, which I've written over here, common denominator of 15 gives us 2 over 15. And when we hit that with the 2, we get 4 over 15. And then, of course, the sine theta term. And then, of course, this term just gives us a 1/2. So very simple antiderivatives. Now, to complete everything with the theta, let's go ahead and run the 2 through. So the 2 times the 1/2 will just give us a 1, and 2 times the 4 over 15 gives us an 8 over 15, and of course the 2 times the 1/2 just gives us a 1. And so now, of course, this is add 1 divided by the new power, so we get sine theta squared over 2, 0 to 2 pi. And here, the antiderivative is the negative cosine, so we get a negative 8 over 15 cosine theta, from 0 to 2 pi. And then the very last one, we just left with d theta, so we get theta 0 to 2. But notice, these all give us 0. When we evaluate sine theta at 2 pi or 0, we get 0. Same for the cosine. In this case, we get the same thing. We get a 1 minus a 1. So it really doesn't matter about all the riffraff out to the left here. The main idea here, or the thrust of this problem, is that these integrals are 0. So like I said, very simple. And then, of course, here we just get theta evaluated 2 pi and 0. So that'll just give us a 0 plus 0 plus 2 pi, and the final answer of 2 pi. So like I said before, Stokes' theorem just gives you an alternative way to compute a line integral. And I'll say, as long as you have some very straightforward circular symmetry, the polar coordinates will usually be the easiest method. Again, there are times when the Cartesian work okay, but this way you avoid ugly radicals, you avoid computations that are much more difficult. Just again, notice the integrals that we have here are extremely simple, and we are done.